Hi everybody. Today you're going to get the first video lesson on an introduction to unit on quadratic functions. This unit is meant for students in Algebra I, but it could be good as a review for students in Algebra II who are just getting going with quadratic functions again, and maybe it's been a while since you've brushed up on it. Let's talk a little bit first about what we're going to be doing here. So I'm going to switch over to a slide presentation. A quadratic function is a special kind of function family, and a function, remember, is a mathematical formula or a rule. It kind of works like a function machine. So if you remember these from elementary school, you've got a little input-output box here that has a rule in it. And you input one value, we'll call it x, it could be anything, and then every time you plug a value into the function rule, it comes out with one possible output. So that's why sometimes we call it f of x instead of y. Sometimes we'll say y equals, and we'll say the rule, especially if we're going to graph it or if we're setting it to a value. But a lot of times we'll use the terminology f of x because this kind of refers to the rule that we're performing on x. We just happen to be graphing it sometimes. So what we're going to try to learn today is what is it that makes a quadratic function a quadratic function? What do you look for in the function rule, in the table, and in the graph that lets you know it's a quadratic function? And then what are some possible applications of quadratic functions so that we know what we're going into going forward? So let's start in with the worksheet. Now I've posted a link to this worksheet on the link for this video. So if you just look down in the description, you can find a link to this Google Doc. Just do File, Make a Copy, and you'll have your own copy of it. And you can follow along with me or do this on your own. You can print it and then fill it out by hand, whatever works for you. I'm going to use annotation tools to fill it out electronically. So we start off with problem number 1. Just to take a look at 3 different possible functions and try to figure out if the relationship we're looking at here is linear, exponential, or if it's something else. So I'd like you at this time to just kind of pause the video and take a look at these 3 tables and try to figure out which one's linear, which one's exponential, and which one's neither of the two. Okay, pause for a moment. Okay, so you may have noticed a few important features of these functions that gave you clues. So the one that's linear might have jumped out to you because you can tell this is linear because it goes up by 3 every time. So if you look at the table, going from 16 to 19, that's plus 3. And the x is changing at even intervals, so that's a big help. That's plus 3. That's plus 3. So every time we go down a row in the table, the slope is 3 because the y is changing by 3 and the x is only changing by 1. So remember, the change in y to the change in x, that ratio is the slope. So this has a constant slope of 3. It's rising at a constant rate. It clearly makes a straight line. And if you played around with it a little bit, you might be able to figure out the function rule. I noticed that 6 times 3 is 18, and then this is a little bit less than 18. 7 times 3 is 21, and this is a little bit less than 21. 8 times 3 is 24, that's a little bit less. So it seems like the function rule is f of x equals 3 times x minus 2. So every time we go to f of x, we're taking the function, the value that's in x, multiplying it by 3 and subtracting 2. So those are the 2 ways that you can tell this is a linear function. One is that the rule has a very clear y equals mx plus b pattern, and it rises by 3 every time. This one, column A, has a really interesting pattern too. You might have noticed that every time we go down a row here, the value from before triples. So this is times 3, and then this is times 3, and then 9 times 3 is 27, and then 27 times 3 is 81. So if you notice that, where every time you increase the x, you have a multiplying relationship going down, that is an exponential function. And the function rule for this one looks like this. F of x equals 3, sorry, I'm drawing incorrectly. That should be a 3 to the x power. And you notice that anything to the 0th power is 1. 3 to the 0th power is 1. 3 to the first power is 3. 3 times 3 is 9. 3 times 3 times 3 is 27. 3 times 3 times 3 times 3 is 81. So this is the exponential function. It's 3 to the x power, where x is however many rows you've gone down in the table. This is the one that stood out as possibly neither. And this one had a really interesting pattern in the table that if you were attentive, you might have noticed. So going down from here from 33 to 46, this is a plus 13. Okay. Going from 46 to 61, that's plus 15. Going down from 61 to 78, that's plus 17. Going down from 78 to 97, that's plus 19. So every time we go up 1 in x, the y changes by a steadily increasing amount. So the slope is changing by a steady amount. Here the slope is 13, here the slope is 15, here the slope is 17. The slope is a linear equation in the case of this table. And you may have figured out, since this is linear and this is exponential, this is the one that's the quadratic. So linear is there, exponential is there, and the something else is here. This is a quadratic function. If you know your times tables, you may have also noticed another interesting pattern. So 6 times itself is 36, and this is not that far off. 7 times 7 is 49, and that's not that far off. 8 times 8 is 64, and that's not that far off. 9 times 9 is 81, and it looks like there's a pretty consistent pattern where every time you square this number, and then you subtract 3, and that's how you get f of x. So this function rule is x squared minus 3. And that is the hallmark of a quadratic function. It has some term in it that is squared, and in the table, its slope increases by a steady amount every time, so the slope's a linear function. So I'll go back to the slide presentation just to give you a couple notes on that. Let's see if I can get that to open. Oh, I have to turn off the drawing tools. Okay. All right. So as we went over, in a linear function, the function looks like this. It's a y equals mx plus b. And in our example, the function was y equals 3x minus 2. So you take the input, plug it into that rule, you get an output. And the result is that the values go up by a steady amount every time, and the graph looks like a straight line. In an exponential function, its function rule looks like this. Some number a times b to the x power. So our function was 1 times 3 to the x power. You plug in an input, you multiply it, you multiply 3 by itself that many times, and that's how you get the output. And in an exponential function, the graph looks like a hockey stick, where it grows really slowly at first, and then it explodes very quickly. In a quadratic function, the term with the highest exponent is x squared. So you'll notice that in all quadratic functions that it's got some term in it where the highest exponent is x squared. So the function that we had was x squared minus 3. Take your input, plug it into the function. 6 times 6 is 36, minus 3 is 33. And we're going to learn next about some other properties of quadratic functions. So like what to look for in the equation, in the graph, and in the table. Quadratic functions are important because there's tons of real-world applications. The biggest examples involve area and circles, so geometry applications, and also many things in physics have to do with quadratic functions. Projectile motion, planetary motion, electromagnetism. There's a lot of things that involve forces and gravity that include quadratic functions, so they're super relevant just for understanding basic mechanics. We're going to go back to the worksheet, and then let's go down to problem number 2, where it asks you to graph what we call the parent quadratic function. So this is the most basic quadratic function you can possibly write, y equals x squared. So it just has one term in it, x to the second power. It's the basic quadratic function. We're going to make a little graph of this, a coordinate graph, by plugging in some inputs of x, figuring out what the outputs are, and then plotting them on a grid. So we'll start filling this out here. I'll do this one with you. We'll start off with -3. -3 squared is -3 times -3, and a negative times a negative is a positive, so this is positive 9. -2 times -2 is positive 4. -1 times -1, positive 1. 0 times 0, super easy. 1 times itself, 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. Okay, so those are our values. I can see my y's, my f of x, are all positive, and my x's are positive and negative. So as I graph this, I'm going to kind of make a little set of coordinate axes here, but I'm going to put the origin. I'm sorry, it's hard to draw straight lines with this. Do your best. I'm going to make my origin kind of down here close to the bottom. And then I'm going to switch color so I can start graphing the graph of this. So we'll start off with -3, +9. On your graph, find 0, 0, and go to -3, -1, -2, -3, +9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and just make a dot right there. Okay? Oh, it zoomed in. I didn't want to zoom in. Stop, stop, stop. Oh dear. Oh dear. Hold on. What have I done? Oh no. Please hold. Okay, it zoomed out again. We try that one more time. I'll try not to double click quite so much. That was horrible. All right, so lesson learned. Let's make my coordinate graph again. I won't be able to make these lines straight. They're still going to be awkward. Okay, and now make a blue dot. So this time I'll be really careful. -1, -2, -3. Oh, I lost my numbers. It was 9, 4, 1, 0, 1, 4, 9. You might be done with your graph by now. I don't know. I'll go ahead and plot these points on the grid while you pause, and then we can compare a graph. Okay, I have finished my graph. Hopefully you finished yours. This is what it ended up looking like. So it looks at first like it might make kind of a V, but if you zoom in a little more closely, it actually makes a smooth U shape. It's kind of a bowl, and this shape that it makes has a very special name. So I'm going to show you a slide so you can see what that looks like. I do have to turn off the drawing tools, so hopefully your graph looked just like mine. Okay. So the graph of a quadratic function is called a parabola. And it makes a distinct U shape. It goes on forever in both directions. So the more you go in the x direction on either side of that minimum point, the higher the y values go, and they just keep on going. Usually the domain is all the x values. You can pretty much plug any real number into a quadratic function and you'll get some kind of output. But for the range, you have a distinct minimum or a maximum. You noticed in our function previously that when we square a number, we always get a positive. So in the case of the parent function, y equals x squared, the range is anything 0 and greater. So it only outputs positive numbers in the case of the parent function. But if you change the nature of the equation, you can change the nature of the graph and also the domain and range. So one thing to notice back in our worksheet is that the vertex of this parabola is at 0, 0. So in that vertex, pay attention to it as we go through some examples so that you can see how it shifts around as you change the inputs of the graph, as you change the nature of the equation. I have a couple of quick pro tips when it comes to using technology. So if you want to type a quadratic function, I'm looking for a place where I can type. If you do Control period, it makes it superscript mode. So you can type x squared by doing x, Control period, and then the 2, and you get x squared like that. Just a random tip. So I'm going to move you on to the next one. Graph the equation y equals x squared minus 3. And so first you're going to make the table of those values, and then we'll plot them on a coordinate grid. And I'm going to pause the video. Before I pause it, just a quick note on order of operations. Exponent first, then subtract. So for this input, for example, you'll do -3 times -3, which is +9, and then subtract 3. Okay? So work your way through the table. I'll do mine while I pause, and then we'll compare answers. Okay, here's what I ended up with. So in my function, I plugged in all of these values for x, and these are the outputs that I got in terms of f of x. So notice my output started going negative in this case, but I still had a very clear symmetry point. the f of x values bottomed out when I got to where x equals 0, and then they started to rise again. So my graph still looked like that classic parabola, but its vertex had moved. So in this case, the vertex of the parabola is at 0, -3, because that's the place where the graph makes a turn and starts going the opposite direction again. That's the clear minimum. Also notice how 0, -3 is reflected in the function. So x squared minus 3 seemed to take the whole parabola and just shift it downward 3 places. So good to know. We're going to go ahead and move on to the next one and see how that graph shakes out. Hopefully you're hanging in there and doing okay. On to the next one. And just so we're clear, on question number 4, our function now looks like y equals x plus 2 quantity squared. When you say a term like this in parentheses and you're raising it to a power or something, I'm just going to type in here how you say it. This function is said x plus 2 quantity squared. So you don't have to say parentheses x plus 2 and parentheses squared. You can say it's the quantity, or you can say the quantity x plus 2 squared. So that little set of parentheses, you say the quantity. Anyway, first you're going to do x, you're going to add 2 to it, and then you take that and you square it. Do parentheses first, then the exponent, just in your PEMDAS rules that you remember, okay? Fill out the table, and then we will do the graph. Notice the table's shifted a little bit. I did that for a reason. You'll see why in a moment. Pause the video, fill out the table, make the graph, and we'll compare. Okay, hopefully you have gotten to this point in your graph. So remember, when you do -4 plus 2, you get a negative number, -2, and -2 squared is +4. -3 plus 2 is -1. -1 squared is +1. And we worked our way down. And then when I graphed these points, I still got that classic parabola. I couldn't graph 216 on my graph. I ran out of room, so I just ignored it. But the parabola has moved again. So it still has the same shape as the other ones before, but this one has shifted to the left 2 points, which is interesting because in the function, you can see the 2 in there, but it's a little counterintuitive because it says x plus 2 squared, and very clearly we have moved the point 2 places to the left. So the vertex of this parabola is 0, -2. There we go. And when we graphed that, when we had the function rule, it was y equals the quantity x plus 2 squared. So another interesting thing to take note of. Hopefully you're getting the hang of plugging and chugging these functions. On the next one, you'll see it's y equals 3x squared. You do the, just like in PEMDAS, you're going to do the exponent first, x squared, and then you're going to take that and multiply times 3. So I'll pause here while you plug in the values for the next one, and then let's compare our graphs. Don't worry about graphing anything that you can't fit on the grid. The idea is just to get the basic shape. Okay, on the next one, you'll notice that this one took on a really different shape. So when you do 3 times x squared, it made those numbers explode and get big really quickly. In fact, I couldn't even graph the x equals -3 and x equals +3 on my grid because I ran out of room. So I was able to fit all of the points in the domain from -2 to +2 on my graph. So the vertex of this parabola is still at 0, 0, but you'll notice it like really elongated and got kind of long and skinny. And so that's an important thing to notice about this quadratic function. So we didn't add or subtract anything, but we multiplied the x squared term by 3, and look what it did to the shape. The vertex is still at 0, 0. Oh my goodness, the drawing tools are not catching up. That's supposed to be 0, 0. I think that's going to erase everything, but whatever. That's at 0, 0, and that one was a longer, skinnier parabola. Okay, next one down. Let's scroll down and see. There we go. On number 6, the function looks a little different, so a quick chat about order of operations before we fill out the table. When you do 0.5 x squared plus 4, you're going to do the math in this order. First, you'll take your x term and you'll square it. Then you'll take that and multiply by 0.5, which means you cut it in half, and then you're going to add 4. Okay? So as I'll do one with you as an example. Yeah. So -3 times -3 is +9. Half of +9 is 4.5. 4.5 plus 4 is 8.5. So that's what you'll put right there. And I know I can do this. Okay, does that make sense? And then -2 squared is +4. Half of +4 is +2. And then +2 plus 4 is 6. Okay, so work your way down the table, fill that one out, and we'll come back in a moment and look at the graph and analyze where the vertex ended up being. Okay, in our function here, we ended up with a really interesting graph. So the vertex of the parabola shifted up to 0, 4, and that 0.5 multiplier in front of the x squared made a difference in the shape as well. So in the previous problem, we had 3x squared, and that made the parabola really tall and skinny. And when you have 0.5x squared plus 4, it shifts it up 4 places and makes it like wider and fatter. So you should notice that this parabola ends up being just a little bit like stretched out and squat, a little huskier than the previous graph. So as you're starting to pick up these patterns and what to notice with the function, the next activity moves you past filling out a table and graphing by hand and lets you use Desmos to graph things electronically. So I'm going to turn off the drawing tools and scroll down a little bit. Oh wait, there's one more. No, we got to do this one first because it really is an important one to plug and chug for you. So you're going to do one more table and graph. Ready? Now, an order of operations note on this equation. When you have a negative in front of a set of parentheses, it's like multiplying by -1. And you do that in the same order you do multiplication. So you'll do parentheses first, x minus 1, square that, and then multiply by -1. So as an example, if x is -3, you'll do -3 minus 1, which is -4. -4 squared is +16. And +16 times -1 is, hold on a second, -16. Does that make sense? I'll try -2 with you as well to get the hang of it. -2 minus 1 is -3. -3 squared is +9. +9 times -1 is -9. So follow the order of operations outlined there. Make your table and your graph, and you're going to see something a little weirder and more interesting with this one. Okay, did you end up with a graph that looked like this one? In this situation, it may have surprised you a little bit to find that you had to move the origin way up to the top of the page in order to get your graph in because all of these numbers ended up being negative. So the domain of this function is still all of the x values. You can plug in any real number you want. But the range of it is anything that's 0 or less than 0. So all negative numbers or 0 are the range of this function. The vertex is at 0, 1, and you can see that in the x minus 1 squared right there. So it's interesting, again, a little counterintuitive, but the x minus 1 quantity squared shifts it to the right one. But that negative multiplier in front of the whole thing inverted the parabola. So it's now opening downward like this instead of upward like this. Negative multiplier, positive multiplier. For the next little activity, I'm going to go ahead and turn off the drawing tools. You're going to complete this part on Desmos. If you haven't used Desmos before, it's a little graphing calculator that you can use online. You just type in desmos.com, and I want you to graph y equals x squared on the little graphing tool, and then start adding these on as extra graphs. So I'm going to write down one of them on a piece of paper so that I remember what it is, and then I'll show you how to add each one as a separate graph. And then all I want you to do in this exercise is draw just like a quickie little sketch of what it looks like in Desmos. Or you can just, observe and take notes. Why can't I find a pen? Hold on one second. Okay, got it. So, for example, I'll graph y equals x squared, and then I'll graph y equals x plus 5 quantity squared. X plus 5 quantity squared. Okay, off to Desmos. So this is when you first load Desmos, you're going to see a red button that says Start Graphing. So click that red button. And then when you get in here, we're going to type in each function as a little separate entry in Desmos so we can see what the graph does. This again is the parent quadratic function. If I zoom out a little bit here, you can see that it's a parabola that's opening upward. The vertex is at 0, 0. And it starts off kind of wide-ish toward the bottom and then very quickly gets large on both sides. So I'll add on to it another graph of y equals quantity x plus 5 squared. So y equals parentheses x plus 5 end parentheses, and then to raise it to the second power, you can do shift 6 to get that little, it looks like a hat, like a little carrot, shift 6, and then I can type in the exponent 2. So that's the graph of y equals x plus 5 quantity squared. And on your paper, you can just draw like a little coordinate grid. So I'll show you what that might look like for me. Use the drawing tools. Okay, so I would draw a little axis like this, and notice that x plus 5 quantity squared shifted it this way, like that. So to the left, about 5 places. That's what the sketch would look like. Keep adding these other functions in and just take note of how they change. Do they change shape? Do they change position? Do they do both? Are they inverted? And then when we come back, let's take a look at all these graphs and we'll come up with some rules for vertex form of a quadratic function. Okay, so if you did all of this, and it looks like I typed in something wrong there, so let me fix it. There we go. If you did all of those functions in Desmos, you ended up with this mess of graphs on here. If you click on the little colorful sine wave next to each function, you toggle it on and off so you can tell which each one is. And so it can be helpful to just like turn all of them off except the one you're interested in and the parent function. So we can see that y equals x plus 5 quantity squared took the parent function and shifted it to the left 5 places. This function, y equals x minus 8 quantity squared minus 5, has the same shape as the parent function, but it is moved to the right 8 and then down 5. Y equals 2.5x squared is at the same vertex as the parent function, but it's skinnier and taller. Y equals 0.3x squared has the same vertex as the parent function, but it is wider and fatter. Y equals negative 2x squared. It's a little hard to see and it's subtle, mainly because mine are the same color, but this is skinnier and taller than the parent function and inverted. And then this last one, y equals negative 0.25 times the quantity x minus 4 squared, shifts to the right 4 places, it's inverted, and it's a little wider and fatter than the parent function. So it leads us to our last little page of notes here. Vertex form of a parabola. So the parent function we remember is y equals x squared. In vertex form, you add a few modifiers to your parabola. So y equals a times the quantity x minus h squared plus k. We played with 3 ways to modify that function. This multiplier a, this thing that we add or subtract from x before we square it, and then this thing that we add or subtract to the whole function after we've done all that math. You may have noticed that as we played around with those numbers, h and k shift the vertex of the parabola. H shifts it to the right or left, and k shifts it up or down. Notice that it's a little bit counterintuitive because whatever h is, for example, if it's x plus 2 quantity squared, it's going to shift it in the negative direction. If it says x minus 2 quantity squared, it shifts it in the positive direction. That's why in vertex form, it's written like x minus h quantity squared. And then whatever you're subtracting, that's the direction you're moving the parabola. And then a is a scale factor. If a is negative, the parabola is inverted. If the magnitude or absolute value of a is less than 1, so it's like a fraction or a decimal, then it's a wide, short parabola. And if the magnitude is greater than 1, then it's a skinny, tall parabola. For further practice, I recommend some exercises on Khan Academy, and I'll put the link to this in the link for the video. On Khan Academy, there's a set of exercises called Quadratic Functions Vertex Form. So you can go over to that set of exercises, watch the video, do a little practice on graphing quadratics in vertex form, and you can also do quadratic word problems in vertex form for a little extra. And then in the next video, we will start looking at other forms of quadratic functions and how sometimes things can look like quadratic functions or not look like quadratic functions, but they actually are. So thanks for listening, and if you have any feedback or questions or need help with any problems, feel free to leave me a comment.